Hey Kim Gang, here's a quick video on using any periodic table to use the octet rule to determine ion charge. And the important thing about this periodic table here is it doesn't tell you the charges of any ions, but all we have to do is think about the pattern in valence electrons and the octet rule. So the first thing that we realize is that the valence electrons go through a simple pattern. And remember, the valence electrons are in the outer shell and they're always in the s and the p blocks. So as we go across the periodic table, we can count 1, 2, 3, 4, 5, 6, 7, 8. And quite reliably, that will be the number of valence electrons in each of those elements. And in your periodic table, you do have the number of electrons in each shell, so it's the last number. And you see all of these are 1. Right? So um, in the first column of the alkali metals, you're putting 1 electron into the s block of a new energy level. And then the next column over, you add the second one, and that's why these all have 2 valence electrons. Okay. We're going to skip through the D and the F blocks. Most elements there have 2 valence electrons, but there are exceptions. And that's because you don't start adding electrons to the valence shell until you start adding electrons to the p subshell, and that happens in the p block. So when the first electron that goes into the p's is the third electron in the valence shell. There's already 2 in the s's, really the one in the s orbital, because there's only one of them. But here you see 3 valence electrons because now there's 1 in the p's. And then when you add a second one to the p's, you have 4 valence electrons, and so on. 5, 6, 7, 8. Right? So remember, the octet rule says that those elements that I just pointed out, for the most part, are going to gain or lose electrons, so they have an octet when they make an ion. And the exceptions are the metalloids, which tend not to make ions, and the metals here, because they have to lose electrons, even if it might be easier for them to gain them. But very reliably in the s block, these elements only need to lose 1 outer shell electron. Okay? And then the next shell in, you see, always has 8, which is a full outer shell. So these lose 1 and make +1 ions. Okay? These lose 2 and make +2 ions. And the only real element that we need to worry about here, because it's the only common one that we would talk about, would be aluminum. And if aluminum loses those 3 outer shell electrons, it has a valence shell of 8. So we have a pattern going from left to right of +1, +2, +3. And that's very easy to remember, but we remember what's behind it. That's how many electrons they need to lose to have a full valence shell by stripping off the outer shell. For the nonmetals over here, it's opposite. Now remember, the noble gases already have a full valence shell, so they don't make ions. So that's like nothing happening there. And that's why they're so unreactive. Okay, but fluorine and everything in the halogen family has 7 valence electrons, so they need to gain 1 and make a -1 ion. Okay, oxygen and its family need to gain 2 and make a -2 ion. That's mostly sulfur, although selenium can do it as well. And nitrogen and phosphorus have 5 valence electrons. They need to gain 3, and I'll make a 3- ion. So the pattern kind of counts backwards here, and they're negative ions. So no ions here, but then -1, -2, -3. And that's an easy pattern to remember, even if you don't know what's behind it, but you should know that it's all about gaining or losing to get 8. So +1, +2, +3, -1, -2, -3. Okay? And remember, the ones in the middle of the periodic table, we're going to learn that they tend to bond covalently, which is an easier way to bond than making ions by gaining or losing 4. All right, so that's it. Know that pattern. You're going to be using it all the time throughout the year.